Now, coming back to what we had discussed the other day, um, we talked of, or we had defined what we called as the transportation problems. Okay, and what we had seen last time was that we need to have sources and destinations. So we could have n number of sources that are supplying things to n number of destinations. Now all these sources in together have limited availability of the products that are going to be transported or supplied, and all the destinations together have demands in total that need to be met with. Okay, because the sources are supplying the products to these destinations and their demands are being met. And we had seen that the availabilities were something like A1, A2, AM, and demands were something like B1, B2, BN, and we had seen that a necessary and sufficient condition for this problem to have a solution was that the summation of AI must be equal to summation of Vj's, J varying from 1 to 1. That means total availabilities must be equal to the total demands. Then only the given transportation problem will have a solution. And if the transportation problem have a solution, then it's a necessary and a sufficient condition. Okay. So whenever availability is equal to demand, we call such a transportation problem to be a balanced transportation problem. Otherwise, it's called to be an unbalanced transportation problem. So one thing is very clear, that whatever method that we have developed or we are going to develop now, they are applicable only to balanced transportation problems. So once you are given a problem to solve, the very first thing that you need to check is whether the given problem is a balanced problem or not. If it's balanced, we proceed on. If it's not, then we balance it. I mean, how that will come up with when I take up an example of an unbalanced transportation problem. So because if it's not balanced, then it depends upon which one is higher. The total availabilities are more or the total demands are more. So accordingly, we incorporate a dummy source or a dummy destination, depending upon which is higher. Okay. Now, once you are sure of the fact that your problem is balanced, the next step is to find an initial basic solution to the given problem. I mean, we have seen how a given transportation problem is converted into a linear programming problem, and that can be solved. We have seen that we have one objective of minimizing the cost with m plus n number of constraints and m into n number of variables in it. Okay. We find that the next step is that we find an initial basic solution. Okay. Now, as I explained last time also, there are various methods to find the initial basic solution, which we are going to discuss today now. Okay. Now, once we have the initial basic solution, then the next step is we check for the optimality of this initial basic solution. That means we check the fact whether the solution that we have obtained is optimal or not. If optimal, we end. That means we stop the problem and we take that as the solution. If it is not optimal, then we upgrade the solution. Okay? That means we convert this basic solution into another basic solution which would improve the optimality of the problem. That means which would further minimize the cost of transportations. Okay, so that is the upgradation of the solution. Once we have upgraded the solution, then again we check the optimality. Okay, if it's optimal, we stop. Otherwise, we further upgrade till optimality is attained. Okay. Now the question mark is, once we have a transportation problem and once we are looking for the basic solutions, the problem is how many allocations can be made so that we get basic feasible variables. Okay. Now, we say that we have seen that there are m plus n number of constraints. Okay. So definitely there would be m plus n minus 1 number of basic variables in it, always. Okay, basic variables means those cells, I mean, the variables here are going to be the cells, the xij's that we have defined, where we are going to make the allocations. So xij's are going to be the allocations in these problems. Okay, allocations means allotting how much should ith source supply to the jth destination. That is an allocation we are making. Okay, so when I say basic variables, that means in a way I'm looking for how many xij's, right? How many xij's means how many non-zero xij's. Because all in the simplex method also we have seen that it is the basic variables that take the non-zero value. All the non-basic variables are zero. Okay, so that means wherever xij is non-zero, that becomes a basic variable, and wherever xij is zero, that becomes a non-basic variable. In other words, we can say that all those cells which get an allocation are the basic cells, and all those cells where allocations cannot be made or we are not making any allocation, they are non-basic cells. If we are not making any allocation, that means the allocations allotted to them are zero. So if we are not making any allocation, that amounts to saying that that particular source is not supplying anything to that particular destination. So basically the allocation is zero in that case, or the value of the variable is zero in that case, so it becomes a non-basic variable. Okay, so if we have m plus n constraints, and if we have exactly m plus n minus 1 non-zero or m plus n minus 1 basic cells or basic variables, then such a solution is said to be a non-degenerate solution. That means it will give you a unique solution. Okay, but in case your number of variables where allocations have been made, they are less than n plus n minus 1, then that is the case of what we call as degeneracy. So it needs to be handled in a different manner. In a way, that means it may lead us to an alternate or infinitely many options. So what is normally done is that randomly any other cell, not exactly randomly, we have methods for that also, any other non-basic variable is given an allocation 0, it is already has an allocation 0, but it is brought into the collection of basic cells, and then we proceed on. Okay, so degeneracy is again something that we are going to discuss later. So we are going to handle the direct cases first, and then we move on to special cases. Okay, so the only thing that we have to check now, again I'm repeating the steps, what we have to do is, number one, we have to test whether my transportation problem is balanced or not. If it's balanced, I proceed on to find the initial basic solutions. Okay, once we have obtained the initial basic solutions by any of the method that we are going to describe, we have to check how many basic variables are there. Okay, if they are equal to m plus n minus 1, we straight away start with the optimality conditions. If not, then we handle the cases the way we are going to handle degeneracy in that case. So this is how the algorithm is going to work. Okay, so one by one, we'll proceed on with all possible cases. So as I said, we'll handle special cases later on. We'll handle the direct cases first. Okay, so I mean, to find the initial basic solutions also, I think last time I told you, we are going to learn three methods. The first is called as the northwest corner rule, or the northwest corner method. The second is the least cost method. Okay, and the third one is the Vogel's approximation method. Okay, now why in this order, I'll tell you. This is Vogel's approximation method. Some books you will see they also call it as VAM. Okay. Now, why this order? It is the it is the it is the ease with which it can be solved, and also the efficiency or the closeness with which these solutions take us to the optimal solution. Okay. Uh, we'll start with the